This is an overview of the paper Bipartite Matching under Communication Constraints. We begin with the abstract model, build the random graph that drives the analysis, state the theoretical results, and meet two algorithms, DB0, the uniform baseline, and 2CGS, the deployable current best. We have a bipartite graph G with n senders on the left and n receivers on the right. An edge from sender U to receiver V means U has at least one outstanding long message waiting for V. The fabric carrying these messages is congestion-free in its core, so the bottleneck is the per-host link. While U is transmitting to V, neither node can do anything else. The set of simultaneous transfers is therefore a matching in G, a set of edges with node 2 sharing an endpoint. The first hard constraint is locality. Each sender knows only its two-hop neighborhood, which receivers it can reach, and how many other senders each of those receivers can reach. Nothing global. The second hard constraint is single round. One exchange of messages, then commit. No multi-round refinement, no augmenting paths. The goal is to produce a matching that is as large as possible under these two constraints. How does the feasible graph arise? The paper models it as a D-out random bipartite graph. The construction has two steps, repeated independently for every sender. Step 1. Each sender U independently draws an out degree D sub U from a common distribution on the integers from 0 to n. Step 2. Conditional on that degree, the sender selects D sub U receivers uniformly at random, independently of every other sender. Each chosen receiver becomes a neighbor. Repeat for every sender, and the feasible graph emerges. The receivers do not choose, they are chosen. A useful consequence: receiver degrees are themselves random. In the limit of large N with the mean sender degree D bar held constant, each receiver's degree is approximately Poisson with mean D bar. The senders are independent and identically distributed. The receivers inherit a Poisson profile. Now mark a matching, a subset of edges with node 2 sharing an endpoint. Even with full visibility, computing the maximum matching at data center scale is too expensive. This motivates a distributed approach with local information and limited message passing. That is the setting we will study. Before the math, the protocol. 1 round, 4 stages: notify, reply, grant, accept. Each sender knows only its own neighborhood. Receivers see only the messages that reach them. Stage 1, notify. Each sender announces a subset of its candidate edges. Choosing not to notify some of them is the thinning step. Counterintuitively, dropping edges can later make the matching larger. Stage 2, reply. Each notified receiver replies, piggybacking its effective degree, the number of notify messages it received. Stage 3, grant. Each sender picks one of its notified receivers and sends a grant. This is the design space. Every algorithm in the family differs here. Stage 4, accept. A receiver may have received multiple grants. Here one of them did. It accepts exactly one. The other grant is rejected. The accepted edges are the matching. So an algorithm in this family is two design choices: which edges to notify, the thinning rule, and which receiver to grant. The rest is shared scaffold. The DB alpha family parameterizes the grant rule by a single number alpha. Sender U draws a neighbor V with probability proportional to the degree of V to the alpha, normalized over its neighborhood. The parameter sweeps two extremes. Alpha equals 0 gives uniform selection. Every neighbor is equally likely. Alpha tending to negative infinity gives a greedy selection. Always pick a minimum degree neighbor. The paper proves alpha greater than 0 is bad and excludes it from the analysis. The optimization target is alpha star, the exponent that maximizes, in the large N limit, the expected fraction of receivers that get matched. Theorem 1 pins down the uniform extreme exactly. Under DB0, the expected matching fraction equals 1 minus the quantity 1 minus the probability of a non-zero sender degree divided by n, all to the n. Two corollaries. If the out degree is deterministic, the limit is 1 minus 1 over e, about 63%. If the out degree is binomial with mean d bar, the limit is 1 minus e to the negative 1 plus e to the negative d bar. Robustness note: under DB0, the matching fraction depends on the sender degree distribution only through the probability that d equals 0. Not the variance, not the tail, just whether a sender has any neighbors at all. The greedy extreme, alpha equals negative infinity, admits a lower bound, not a closed form. Theorem 2 states it in the Poisson regime, a sum over s of e to the minus d bar times d bar to the s over s factorial times 1 minus f of s, all raised to the s. The function f is expressed through the generating function of d in the Poisson tail. Between these two extremes lies alpha star, which can be characterized numerically. Simulation matches both theorems to within Monte Carlo noise. dB0 is the parameter-free baseline. Can we do better? Empirical study of the dB alpha family surfaced a heuristic, 2CGS, two-choice greedy selection. It is not optimal in any theorem, it is what simulation found to be the current best. It makes two changes to dB0, both at familiar stages of the protocol. Change 1, thinning. At the notify stage, each sender retains the minimum of 2 and its actual neighborhood size, so at most 2 outgoing notify messages. The chosen edges are uniform, the rest are discarded. Change 2, greedy grant. Among the retained edges that came back as replies, the sender grants the one whose receiver has the smallest degree. Ties broken uniformly, accept is unchanged. 3 messages, no parameter to tune. Watch the same small graph again. Replies come back with degrees. Each sender picks the minimum degree reply and sends a grant on that edge. Collisions on popular receivers do happen, but they are rarer than under uniform selection. The accepted edges form the matching larger than the dB0 baseline on the same graph. The packet-level evaluation runs on a realistic leaf-spine fabric. 9 top-of-rack switches, 4 spines, 16 hosts per rack. 100 gigabit per second on the access links, 400 gigabit on the uplinks. 2 production traces drive the workload, IMC10, a data center capture, and SGD, a distributed training trace. Here is the headline metric. The stability region, the largest load at which long message flow completion time stays bounded. iSlip saturates somewhere between 40 and 50%. dB0, the baseline, holds to about 50%. 2CGS extends the stable region to roughly 60% across both traces. The paper makes a stronger claim. The stability region is largely a property of the algorithm, not the workload. The bars look similar for IMC10 and SGD. So 2CGS is parameter-free, costs the same 3 messages as dB0, and matches more pairs per round.